x is given by hyperbolic cosine, t is given by hyperbolic sine. Well, it's generically true that for any theta, hyperbolic cosine of theta is bigger than even the absolute value of hyperbolic sine of theta. And as a result, for any place where these coordinates make sense, I have that x is bigger than the absolute value of t. In other words, I'm off in this right-hand wedge. So you might say, well, that's kind of silly. I mean, yes, it's a nice way to illustrate these black hole-like properties, but wouldn't I also like to describe the rest of the space-time? What do I do about observers, for example, who fall through the horizon? How do I describe them? Well, I'll just mention quickly that one can introduce an analogous coordinate system in this part of the space-time, again using hyperbolae, like so, and hyperbolic angles. For that case, I guess I'll write this down here. Since clearly the hyperbolas are now separated by time and not by space, let me call this coordinate tau. And I'll introduce another hyperbolic angle, which, for the lack of anything better, I'll call chi. Okay. Then you can introduce these coordinates with very similar relations that we saw before. You can define them through, in this case, t is equal to tau times the hyperbolic cosine of chi, and x is equal to tau times the hyperbolic sine of chi, basically just swapping x and t from what we had before. And if one works through the metric, one finds something very similar. One finds that in this case, the metric is ds squared is minus d tau squared plus tau squared d chi squared. Okay. All right. It's worth pausing to interpret this again. What this says, recall that in the previous case, this factor of xi here meant that the amount of time which passed on different world lines was sort of different. There was a redshift, and less time passed close to the horizon, more time passed farther away. Well, that arose because the xi was in front of the time part, which was theta there. Here, the similar coefficient is tau, which is in front of the chi part. Okay? So what that says is not that we have a measure of time which changes in space, but that what we have is a measure of space that changes in time. In other words, if I consider the same hyperbolic angle, like that one, at one value of tau on one hyperbola, and compare it with the same angle on a later value of tau, what you find is that, in some sense, this coordinate system describes this space as having expanded and is now larger up there. So this coordinate system makes Minkowski space look something like an expanding universe, okay, because the size of space changes with time and grows. Jeff? It's the same thing. The milne is usually a quotient of this by some discrete group. Yeah, but it's the same metric. It's using the same boost invariance of the space-time. Right. Yes, and so Jeff has brought up this wonderful point that we've now made contact with a very large number of recent papers in string theory, which have been all about this metric. Okay, so you're all doing very well. All right. So now, that was just Minkowski space viewed in a different way. And again, the use of this is that in your studies of black holes, either in my lectures or elsewhere, you will see a number of formulae that should remind you of either this, or things that are much like them. When you see such things, you can say, aha, these may look a bit strange, but I can figure out what's going on by realizing that if they're exactly like this, they simply encode Minkowski space. And so I can just look back at this picture and figure out everything that I want, because I understand Minkowski space. Okay? All right. Okay, good. So now what we want to do is take this metric and show you how it relates to a black hole. Okay? Now, how am I going to do that? Well, So we're going to go from what's called Rindler space, well, from Minkowski space to a black hole. And the way we're going to make this connection is I'm going to claim, and we'll see, that these two spacetimes are identical, or at least essentially identical, near their horizons. Well, except for one thing, which is that the Minkowski space I've been using so far is a two-dimensional space, and I'd like to discuss a 3 plus 1 dimensional, or a 4-dimensional black hole. If I could use, that was white. Yes, this one came out better. I'm not quite sure why. Okay. How's the orange? Can you see the orange? No, not too well? All right, I'll avoid the orange then. Let's say the yellow seems to work very well. Let me try that. Okay. So I want to take Minkowski space and make it into a black hole. And the first problem, as I've mentioned, is that the dimensions don't match right. I've talked about two-dimensional Minkowski space, and I want a four-dimensional black hole. So what am I going to do? I'm going to add in some more parts of the space-time. I'm going to do it in a very simple way. What I'm going to be interested in is called the Schwarzschild black hole, which is a fundamental property that it is round, or in more technical language, spherically symmetric. Okay? So in other words, it's a round object, and if I have a round object, I can always draw spheres around the round object. So basically, it's the sphere which is missing from my description so far. I have already a time direction, and I have already a measure of distance away from the horizon. And of course, if the black hole is there, then if I walk away from it, that's away from the horizon. So what I'm missing so far in my analogy is, again, if this is the black hole, I'm missing some notion of where I am on some kind of sphere around the black hole. This would only tell me, again, where I am in time or how far away I am. So the first thing I want to do is say that, all right, I want to consider not two-dimensional Minkowski space. Let's see. Two-dimensional Minkowski space is often called R1, 1, because it has one space and one time direction. So I like to say that I want to consider not R1, 1, but instead, let's replace that by the same thing with a sphere. Okay. So I wrote this for the mathematicians in the audience. If you're not a mathematician, this means take two-dimensional Minkowski space and at the same time consider a bunch of spheres. So in that case, what that means is that we now measure distances using our previous metric, which was minus c squared d theta squared plus dc squared. And we also have to add in some kind of metric to represent the spheres. For those of you who have gone through this before, you know what a metric on a sphere looks like. Those of you who don't, it turns out it doesn't matter. So I'm just going to write this d omega 2, which is a symbol which means the metric for actually a unit sphere. Okay. I forgot one thing. So just to keep track of things, this is going to be the metric for a unit sphere. The sphere I add in may not have size 1, may not have radius 1. It may be bigger. So let me also add a factor here, r squared, where r represents essentially the radius of the sphere. So I have a sphere of radius r. All right. Good. All right. So this is the next step. But I want to generalize this even a bit more because, again, if you read my claim in detail, it says not that the black hole is going to be identical to this space-time, but that they're identical near the horizons. Okay? So I want to imagine that I could take the metric for a black hole and sort of expand it in a Taylor series around the horizon. And that this would be the first term, or the zero-order term, then there could be corrections to it. So more generally, or in more detail, my claim is that the black hole is of the form ds squared equals minus c squared d theta. Let me first just copy the previous line, and then I'll amend it. Oops. So here I've merely copied the previous line. And the generalization is that I'd like to add in some as yet unknown function f here, which will be a function of how far away I am from the horizon, and will be constrained to satisfy f of c is 1 at the horizon plus some correction of order c. Okay. Similarly, for a black hole, question? Sorry. For the black hole, I'm going to let this radius depend on position. Because after all, if I have a black hole here, well, let's say the black hole is here, then if I draw this sphere around the black hole, one fairly close, it's fairly small. But if I draw a sphere farther away, it's a much larger sphere. So clearly, the size of the sphere depends on how far you are from the black hole, so we'll allow this to depend on c. Okay. Good. All right. So that is my claim. And in fact, if I convince you of this, if I show you a black hole metric and manage to write it in this form, then that will prove to you that the black hole horizon is exactly like this horizon in Minkowski space, at least so far as is concerned things that are close to it. Okay, because we will basically embedded the one horizon into either space-time. All right. How am I doing on time? Good. But in the general spirit of my plan for this talk, let me not immediately jump into calculations. Let's take a step back and understand a few things about this metric or this space-time. Okay? That is to say, let's see if we can understand a few things about black holes, a few more things about black holes, without even worrying about the detailed form of these functions, but just understanding that it's something of this form. Okay? What I want to do is go back and once again consider the horizon, which we already know is going to be a light ray along this line c equals 0. Now, in fact, because I've added in this sphere, right, the horizon is not just one light ray anymore. It's now an entire sphere of light. So you should imagine that c equals 0 is now, well, there's some sphere in the space-time, and you imagine that at every point on the sphere, you have a light ray going outward, and that sphere of light is the horizon of the black hole. Okay? Now, let's ask, in the black hole space-time, what happens to that sphere as the light rays move out? Okay? Actually, let's take a simpler case first. Let's go back to this simplified metric, where I haven't made anything depend on distance yet. If I go back to this metric, where I've only taken some sphere of some fixed size r and added it into the space-time, okay, then what happens to that sphere of light as it moves outward, quote, away from the horizon? Does it get bigger, smaller, stay the same size? This is the audience participation part of the lecture.